All right, it's 8:30. Let's go ahead and get started. Hi, good morning, everybody. How's everyone doing today? Doing good, doing good. End of week 3, so I know things are probably ramping up. Okay, so today the plan is we're going to finish up our lecture notes on second order ODEs, and so we have just a couple more examples on undetermined coefficients to do, and then we have to talk about resonance a little bit as well. Okay. Announcement I want to make is that we finally have kind of all the paperwork done for the tutor for this course, and so if you need additional help outside of office hours, we have a tutor. His name is Justin Diamond. Okay, it's kind of funny that if you wanted extra help in 308 and you wanted to get it from someone other named Justin, well, too fucking bad. So both of us are named Justin, but Justin's great. He's a student in one of my courses this semester. He's a graduating senior, so he's going to do a fantastic job. So his hours are posted there. So he is tutoring on Tuesdays and Thursdays from 12 p.m. to 2 p.m. and Fridays from 9 a.m. to noon. Okay. He does his tutoring over Zoom. And so if you want to speak with him, then the Zoom link is on the Canvas site. And he has a password as well. And so you can view all of that on the Canvas site. Okay, but I just want to let you know that the tutoring is available. And I guess the first one will be today. And so the hours line up nice because my office hours today are from 10 to 11. But that time doesn't work out for you. You can talk to Justin 12 to 2 today. Okay. All right, another announcement. I checked the Discord channel this morning. I know there's a typo in my solutions for problem 2B. And so I'm gonna work on fixing that later today. Okay. But there is a typo on that one. So if you're getting a different answer on problem 2B than when I have posted, then don't worry about it. But I'm aware that there's an issue, and so I'm gonna be fixing that later. Okay. All right. Any other questions before we get started for today? Okay. All right. So let's go ahead and get started. All right. And so we are right in the middle of solving non-homogeneous second order ODEs with undetermined coefficients. Okay. All right. So remember, the big difference between homogeneous and non-homogeneous ODEs is that we now have a right-hand side functional term. Okay? So if we look at our typical equation, we get y double prime plus p y prime plus Okay. Good. The big addition here is that we have something on the right hand side. So we have R of X, where this R of X here is often called the forcing term. Or the input term. And remember, the reason we call it the forcing term or input term is because usually physically what this represents is some kind of external forcing that you're applying to the system. Okay. Or if you think back to homework one, we had the battery. Okay, so the battery is basically a way to provide internal charging or external forcing to your circuit. And the way we represented that was with a non-homogeneous forcing term. Okay. All right. And so the way we're solving this is we are basically doing like a guessing method, and then kind of fixing our guess afterwards. Okay, so the main method is undistorted coefficient. And so the idea with this method is that we're going to guess a form for the particular solution. And our guess for the particular solution, we choose it in a way such that it looks like the forcing term. Okay, so it has a kind of the same functional form as the forcing. And then once we do that, we basically just take derivatives of that guess and then plug it back into the original equations. Okay. That was kind of the methodology that we're working with. So we basically, we look at our equation, we look and see what the non-homogeneous term looks like, what the forcing term looks like. We make a guess based on the form of that forcing function, and then we just plug it back in. Okay. So I think, last thing we did in lecture on Tuesday was we did kind of a simple example of this with polynomial. Okay. All right, so I have two more examples that I want to do today. Both of them, the first one is kind of more of a special case. The second one is kind of a bit more of a complex example, so that you can kind of see the whole process going through. All right, any questions on this? This is just kind of a recap from last time. Okay, all right, so let's go ahead and move on to the next example. All right. So this example will say it's y double prime plus 3y prime plus 2.25y is equal to minus 10 e with a minus 1.5x. All right, so right away, we see that we have a non-homogeneous term. Okay. You can see that the right hand side here is not equal to 0, and so it's equal to minus 10 e to the minus 1.5x. And so we know that we are going to need to solve for the particular solution. But this one is a bit of a special case, and you'll see why in very, very soon. And so in these cases, we have to do something a little bit extra to our guess to make sure that it's linearly independent from our homogeneous solution. Okay. Step one. And so whenever you have a second order ODE, whether it's a homogeneous equation or a non-homogeneous equation, our first step is always going to be to solve the homogeneous part. Okay. Okay, so the homogeneous equation is basically just our differential equation, except that we just set the right-hand side equal to 0. Okay, and so we have y double prime plus 3y prime plus 2.25y is equal to 0. All right, so just like we usually do, we're going to replace this with the characteristic equation. Okay. And so the characteristic equation is lambda squared plus 3 lambda plus 2.25, all that equal to 0. Okay. You can find the roots of this equation, so you can plug into the quadratic formula, or if you're, if you're a factoring savant, then you can do this by, by looking at it. And what you'll see from this is that we actually have a double root, and so our factorization ends up with the following. We end up with lambda plus 1.5 squared is equal to 0. Okay. That tells us we have a double root. And that is equal to -1. Okay. All right, so let's go ahead and form our homogeneous solution. So YH of x for the double root. First, we have C1 e to the -1.5x. And for our second solution, because it's a double root, remember we're going to use our multiply by x term. Okay, just to make sure that our second solution is linearly independent from the first one. And so this right here is our homogeneous solution. Okay. Right. So that's just, just kind of just a very quick, review of just how we did the homogeneous. Any questions on this here? Okay, so that's the homogeneous part. Step two. Step two in our quest for the full solution, we now need to start solving for the particular solution. Okay, so step two here is going to make a guess. Okay, so we're going to guess a form for the particular solution. All right. So let me write down the forcing function. Okay. And so for this problem here, the forcing function is just whatever on the right-hand side. And so our forcing function in this case is -10 e to the -1.5. Okay. All right. And so using our method of undetermined coefficients, what we would say is that our form for a particular solution should look very similar to this forcing function. And so based on this, we're going to guess yp is equal to big A. And it's going to be an exponential function. It's going to be an exponential function with the same exponent. Okay, so we can see that our input function here is -10 e to the -1.5x. That means our guess should also be an exponential function with an exponent of -1.5. Right, so pretty smooth sailing so far. All right, but we have an issue here. And so let's look at the form for the particular solution. Okay, so our guess for the particular solution is just an exponential function, e to the -1.5x. Okay. But we have a problem. Our homogeneous solution also has e to the -1.5x. Okay. And so if we were to kind of move ahead with this guess, then we would run into an issue because this is not linearly independent from the homogeneous solution. So that's an issue. Okay, because remember, whenever we do any kind of linear combination, which essentially that's what we're doing here too. So we're taking our particular solution, we're going to be adding it to our homogeneous solution. They need to be linearly independent from each other. Okay, so this guess here is not going to work. What we can do is we can modify this. We can modify it so that our guess is linearly independent from our homogeneous solution. Right. And so let's come up with a new guess. So we still like this form, and so we still are kind of we see that our input function here is e to the minus 1.5x. So we want to kind of retain that. But we want to modify it so that we're linearly independent. All right. So I'm going to start with our usual trick. And so, whenever we have a repeated solution or whenever we have something that's not linearly independent, our usual trick is that we can just kind of multiply this by x. Okay. All right, so let's do that. And so let's say that our guess now is ax e to the minus 1.5x. Unfortunately, this also will work because if we look at the form for this particular solution, this is also in the homogeneous solution. And so this is also not going to work. Okay. But that's okay. So, all we have to do is just, take our usual trick and just do it again. Right. And so we're going to multiply it by x one more time. And so our guess for the particular solution is going to be x squared e to the minus 1.5x. All right, and then finally we arrive at a function here that's linearly independent from our solution. So basically the point of this example is that if you're getting a particular solution that's of the same functional form as your homogeneous one, just keep multiplying by x until it's not that. Okay. Okay. So now we have our guess, and so now this one is good to go. All right. So now that we have our guess, let's continue. So let's take derivatives. And plot back. Okay. So first, let me take yp prime. So I'm going to take our guess here for yp and then take the derivative. Okay. I'm going to factor out the constant a on the front just because that's just a constant. Okay. The unfortunate thing with the multiply by x trick is that we now have to differentiate with product rule, so it is a little bit annoying. It's a little bit extra work. Okay. And so our first derivative here, first we're going to take the derivative of the first, 2x, minus 1.5x. Then we're going to take derivative of the second, so that's a minus 1.5 x squared e to the minus 1.5x. We'll just use product rule for that. And then y double prime. We're going to have to apply the product rule twice. Okay, so that's 2 e to the minus 1.5x. Minus 1.5 times 2 x e to the minus 1.5x. Okay. Minus 5 times 2x e to the minus 1.5x. Plus 5 times 1.5 x squared e minus 1. Let me simplify that second one. So I was just kind of doing that just by. And so if you simplify that second one, what you get is a. I'm going to factor out an e to the minus 1.5x because that is a constant. That's a factor for all the terms there. So we get 2 minus 6x plus 2.25 x squared. YP. Okay. So now we have our expressions for YP prime, YP double prime. Let's plug this back into our original equation and solve for the constant A. Okay. And so our original equation, down again. Our original equation was y double prime plus 3y prime plus 2.25y equal to minus 10 equal to minus 1.5x. Okay. So everywhere we see y or y prime, let's go ahead and plug into that. Okay, so yp double prime is going to go here, yp prime is going to go there, and then yp is going to go in. Okay. All right, so we plug it back in. We get is a e minus 1.5x times 2 minus 6x plus 2.25 x squared. Okay. Plus 3 times a e to the minus 1.5x times 2x minus 1.5 x squared plus 2.25 x squared e to the minus x. All this is equal to minus 10 e to the minus 1. Right. And so, there is a lot to plug in. So make sure when you're plugging in here, you're kind of careful because it's kind of easy to miss a negative sign or miss a constant here or there. And so I do it all the time. And so just kind of be careful with plugging in. All right, well, let's go ahead and simplify this. And so we can see on every single term here, we have an e to the minus 1.5x. Let's go ahead and cancel out all of those. And then let's group like terms. And so let's do the constant term first. And so for the constant terms, we have 2a.
Sir,
Yeah,
should there be a constant with 2.25?
there should, yes. Thank you. Thanks for catching. Right. So that is that's the constant term. Now let's do the x terms. And so the x terms, we have a minus 6a plus 6a x, okay. And then let's do the x squared terms. And so x squared, we have 2.25 minus 5 here plus 2.25 from the last term. I'll multiply by a. Right. So of course, for the x terms, we have minus 6a plus 6a, so that's going to cancel out. For the x squared terms, we have 2.25 plus 2.25 minus 4.5a. So all of them cancel out. Okay. And so all that we're left with is 2a is equal to minus 10. So that tells us that a is equal to minus 5. Right. So now that we have A, we can solve for YP. So YP is a minus 5 x squared e to the minus 1.5 x. Okay. So now that we have YP, let's go ahead and form our full solution. Our full solution is going to be the sum of YH plus YP. And so YH is C1 e to the minus 1.5 x plus C2 x e to the minus 1.5 x. And then YP is minus 5 x squared e to the minus 1.5. These could be, a decent amount of work. So definitely, definitely don't underestimate these problems. Even the ones that look fairly simple, it takes kind of a bit of work to take the derivatives, plug it back in, and then solve for them. Especially for the next one. So the next one is going to be a little bit tedious too, but we'll work over it. All right. Any questions on this example? Yes.
So would this have worked if we guessed for the particular solution like x cubed instead of x squared?
It would work too. And so what you're going to see is that basically all the higher order x terms are going to cancel out when you plug it back in. It's just going to end up just being a bit more work for you.
Okay.
Yeah, question.
Can you explain again why you guess had like an x squared?
Yeah, sure. Yeah, so the reason we had an x squared for our particular solution is that we want to make sure our particular solution is independent from the homogeneous solution. So our homogeneous solution had an e to the minus 1.5 x. And so, we can't guess that for the particular solution because that would be the same kind of functional form. And so the first thing that we would try is that we would just multiply by x. Okay. And so we would take our particular solution, multiply just by x by itself. This would work. Okay. So that's normally the first thing you would do. So you basically, you want to make sure that your guesses are all kind of independent from each other, linearly independent. And so you multiply by x. But then, you look back at our homogeneous solution and we have this exact functional form. So x e to the minus 1.5 x here and here. And so that means that guess can't work either. And so we need to multiply by x one more time. And so we got x squared. Yeah, so this is pretty rare. And so, I chose an example just, with not only a double root, but also a particular solution of the exact same form. So this is rare, but this is kind of the worst case scenario. You kind of just keep multiplying by x until you get an independent solution. Yeah. All right, any other questions on this example here? Okay. All right. Oh, by the way, let me check. If you're on Zoom and you're talking, I apologize. It's like the audio might have been off, and so if you have a question on Zoom, don't just if you need to just stop me, just type in the chat, just stop, and then I'll just pause real quick and I'll wait for you to type out. Okay. So I know it can take a while to type out. Okay, all right. So let's do one more example. And this is going to be an example with multiple terms in the forcing function. All right. You have y double prime plus 2y prime plus 0.75 y equal to 2 cosine x minus 0.25 sine x plus 0.09. Okay. We have quite a complicated forcing function here. But what you'll see is that, we're just going to follow the same process as before. It's going to be a little more work because our guest is going to have 4 terms. All right. So let's start. So, for our first point of action is always going to be to solve the homogeneous equation. And from the last example, you can kind of see why. And so the reason we solve the homogeneous one first is we need to make sure that we don't have any conflicting terms. Okay. In this case, it's not going to be an issue because we don't have any exponential terms in our forcing function, but it's always a good idea to solve the homogeneous portion first. So the homogeneous problem is y double prime plus 2y prime plus 0.75y equal to 0. Okay. We form a characteristic equation. So the characteristic equation is lambda squared plus 2 lambda plus 0.75. And if you factor this, use the quadratic equation, we actually get two real roots. And so lambda 1 is equal to minus 1/2. And lambda 2 is equal to minus 3. All right, so we can get our homogeneous solution to C1 e to the minus x over 2 plus C2 e to the minus 3x over 2. Pretty straightforward. Step 2. Step 2 is we're going to guess for yp. Okay. And so we need to guess a formula for the particular solution based on the form of our non-homogeneous term. Okay. All right. So if you look at our non-homogeneous term here, or forcing function, we have two contributions. So we have contributions from a sinusoid, so cosine and sine. And then we have a polynomial function as well. Okay, so that means our guess for our particular solution has to contain all of these components. All right, so YP. First, we're going to tackle the sinusoid, and so we have a cosine and a sine. Okay, so we have a cosine x plus b x. Okay. Remember, when you're choosing sinusoid, you want to make sure that the frequency that you're choosing is the same as the forcing function. And so in this case, our frequency is 1, and so that's why we have cosine x and sine x. All right, and so to this, we're going to add the polynomial terms. Okay. Luckily, in this case, we just have a linear function, and so for a linear function, we would just need cx plus d. These two contributions, the a and b terms, come from the sinusoid. The and d terms, this comes from the polynomial. All right. Any questions on how we came up with the guess for YP? Yeah.
So it takes care of both the sine and cosine because they have the same like number inside, because if it was like cosine or sine of x and then cosine of 2x, so do we need two separate ones?
You would, yes.
Okay.
Yeah. So if the equation was 2x right here, then we would actually need two different sets of sinusoid to handle both of those. So we have a cosine 2x plus b sine 2x plus c cosine x plus d cosine. So yeah, that would be quite more deal. Our question in the chat. Let's see. You got different roots. Let me check, because this is an example I took from the book, and so it should be right, but we can double check here just to make sure. And so we have lambda 2 minus b 2. That's the root b squared, which is 4ac. So 4 times 3/4, all divided by 2. And so we have a second. This is a -1 plus and minus. Square root of 4 minus 3 is 1. 2. And so we have a -1 plus 1/2, which is -1/2, and then -1 minus 1/2, which is -3, 2. So should be right. Yeah. Okay. Good. Okay. All right. So let's go ahead and take derivatives of this and plug in. All right. And so we have yp prime. And so let's take the derivative. So we have a derivative of a cosine x, so that's minus a sine x plus b cosine x. Okay. We take the derivative of cx plus d, we end up with just c. Okay. So the d is just going to go away because it's just a constant. And then we have yp double prime. Yp double prime is just a minus a cosine x minus b sine x. Alright, so let's take these as well as our yp and plug. Okay. Okay. All right, so our original equation is y double prime plus 2y prime plus 0.75 y equal to 2 cosine x minus 0.25 sine x plus 0.05. Okay, so let's plug in. So first we have y double prime. So y double prime is a minus a cosine x minus b sine x plus 2 times y prime minus a sine of x plus b cosine x plus c. And then we have 0.75 multiplied by y. And so it's 0.75 times a sine x plus b x plus cx d. This is equal to the right hand side. 2 cosine x minus 0.25 sine x plus 0.09. Watch right now, so I'll pause here for a second. Okay. All right. So now our next step here is to kind of distribute any of the constants and group the like terms. Okay, so we're going to group the like terms together. So it's a little bit tedious, I know, and so it takes a while to kind of distribute this and group them together. But just for the sake of time, just because I want to make sure that we have enough time to talk about resonance today, because resonance is part of the homework. I'm going to go ahead and kind of skip towards the end. Okay. So this is after a few steps. And I apologize for this, usually I always used to hate it too in math courses when the professor just like, oh, just do the algebra, it's easy, I know it's not easy, it's tedious, I get it, you know. And so I'm not skipping it because I think that, you know, that's easy or not, it's just, you know, it's more kind of mechanical, it's kind of more time consuming. And I kind of wanted to focus on other things in the class, but, you know, if you ever get confused with these kind of examples where I'm skipping steps, you know, please don't be afraid, you know, you can always send me an email. You can always come to office hours and I'm always happy to kind of show you the whole. But in the lecture, you know, the reason I do this is just to kind of make sure we can, you know, get to kind of the important parts. Okay. And so when we kind of, you know, do all that kind of algebra there, we end up with the following. The cosine x. Okay. And so the terms for this are going to be minus a plus 2b plus 0.75 a plus sine of x times minus b minus 2a plus 0.75 plus x. Yes, the x term is just 0.75 c plus the constant term 2c plus 0.75 d. And all this is still equal to 2 sine x minus 0.75 sine x plus 0.75. So that's just the result of, you know, again, you know, distributing, you know, taking the upper equation here, distributing all the constants and just, you know, grouping the terms. So it's a lot of bookkeeping, very tedious, and also, you know, probably the most likely parts where I make mistakes. And so, you know, if there's ever mistakes in the homework, it's probably because I missed a negative and something like this. Okay. So the nice thing is that we're just about done. And so basically now that we have it in this form, we can equate the like term. And so first we have the cosine term. Okay. And so based on this equation here, we know that minus a plus 2b plus 0.75a is going to be equal to 2. Next we have the sine term. And so this minus b minus 2a plus 0.75b is going to be equal to minus 0.25. Okay, then we equate the x term. And so we know that 0.75c is going to be equal to 0.09 on the right hand side. Finally, we have the constant term. And so since the constant term does not show up on the right hand side, we're going to set that equation equal to 0. All right. And so if we use these 4 equations and we solve for our 4 unknowns, we get that a is equal to 0, b is equal to 1, c is equal to 0.12, and d is equal to minus 0.2. And so we plug all those in, then we get our particular solutions equal to sine x plus 0.12x minus 0.2. Okay. And so now that we have our particular solution, we can form our full solution. Y of x, 2, yh plus yp, and that's equal to C1 e to the minus x over 2, plus C2 e to the minus 3x over 2, plus sine of x plus 0.12x minus 0. And so in this problem, just like the previous example, you know, I didn't give you any initial conditions. But if I did give you initial conditions, you would apply it. Remember to apply initial conditions on the full solution. Okay. Any questions on this example here? All right, so we did 3 examples with undetermined coefficients. So we did one at the end of class on Tuesday, and we did 2 today. So hopefully, you know, that gives you kind of a good kind of breadth of examples to help you out with the homework. All right, so the last topic that I want to go over in second order ODEs, and this has to do with problem 4 on the homework, is this idea of forced oscillation and resonance. Okay. So resonance is a very, very interesting phenomenon. It's something that, you know, if you kind of just look at it in a vacuum, it almost seems like magic, because, you know, if you can achieve resonance in a system, it almost seems like you're adding kind of an infinite amount of energy to a system, which you know, which should seem like it kind of violates all the laws of physics. Okay? And so I believe in the homework, I think in problem 1, I asked you a question about shattering a wine glass, right? And so kind of a unique talent that a lot of people have is that if you sing at a wine glass at a very particular frequency, a very particular pitch, you can actually shatter the wine glass. And some people think, you know, I think some people usually think when they see that is that you have to have a very loud voice to make that happen. So you have to have a very loud voice, and that forces the wine glass to break. But that's actually not the case. You can actually cause a wine glass to break with a very kind of soft voice if you kind of know what you're doing. Okay. And so that it has to do with resonance. Okay. And so the reason I kind of waited until now to talk about resonance is that it very much has to do with what we just kind of finished discussing. So it has to do with non-homogeneous second order differential. Okay. And so sometimes, you know, sometimes our forcing term is going to be a sinusoidal function, very much like the last example. Okay. And so our R of X sometimes is something like this. I'm just going to use cosine for now, just for the sake of, you know, saving my hand from writing too much. But, you know, you could easily replace this with a sine term as well, or even a combination of cosine and sine. All right. And what I want you to focus on for now is the fact that, you know, this forcing function had a particular frequency. Right? And so I'm going to give that symbol omega here. And so that symbol here, I'm going to call this the forcing frequency. And so the forcing frequency, that's basically going to be the frequency at which we're going to be applying our external force to the system. Okay. I think last time, you know, we talked about an example for a swing. Okay? And so if you're sitting on a swing on a playground and you want to go higher, right? The way that you kind of do that is you kind of kick your legs out, you kind of pull them back in at a particular rhythm. Okay. And so, the rhythm at which you're kind of kicking your legs out and pulling them back in, that's basically going to be the forcing frequency. Okay? So it's the frequency at which you're kind of externally forcing the system. And so the idea with resonance that if the forcing frequency if the forcing frequency is chosen such that it matches some of the natural parameters of the physical system, if that happens, right? If you kind of find that magical frequency that matches your physical system, then what's going to happen is that your output or your solution is going to have very large magnitude oscillations. And so when this occurs, this is often called resonance. And so visually, what it looks like, that statement right there is kind of has a lot of math jargon, but visually, kind of what it looks like is that it almost looks like a crescendo that's happening, right? And so you see the oscillation, and you see them kind of steadily get bigger and bigger and bigger until usually what happens is that the physical system can't kind of sustain those oscillations. So have you guys seen the video of the Tacoma Narrows Bridge before? Yeah, so Tacoma Narrows, just to kind of sum it up, was a kind of a drawbridge, and it was very poorly designed, although not maliciously. It was just we didn't really understand revenue. And so basically, what happened with the bridge was that wind would blow and it would hit the bridge, and it would kind of vibrate the bridge, but that vibration would kind of match the natural frequency of the bridge, and what would happen is that the bridge would just kind of like just kind of go crazy like this. Right? If you haven't seen the video, it's quite something. And so I don't think we have time to show it today. Maybe at the end if we have some time, but definitely look it up if you haven't seen it. Definitely look up videos of this if you haven't seen it. And so the idea is that every physical system has a natural frequency. And so what the natural frequency is that it's if you were to just kind of force just kind of provide an impulse forcing to the system, then it would just vibrate naturally at its natural frequency. Okay. And so resonance occurs basically that when you apply a forcing frequency that matches the natural frequency. So when those two are kind of in line, that's usually when resonance occurs. And we'll kind of see how that is mathematically in a second. Okay, so let's look at this mathematically. So let's look at let's go back to our mass spring system, mass spring damper. Our mass spring damper was M y double prime plus C y prime plus K y. So I'm replacing the constant for the damping constant. So I know we used B before, but I'm gonna use A and B for something else. So I'm switching the damping constant to C in this case. Okay. And let's say that this is equal to an oscillating forcing function. This will be equal to F0 cosine omega. Okay. So this is kind of the baseline for every kind of resonance system. So you have kind of a physical system, which you can represent as a mass spring damper most of the time. And then you have the forcing function, which is going to be of a particular frequency. Okay. All right, so what we're going to do is we're going to solve the system, and we're going to see how the amplitude of the outputs are going to be magnified if omega is chosen to be a certain value. Okay. And so what we have here is a non-homogeneous system. Okay. And so what I'm going to do, and so what we're going to do is we're going to solve this using our method of undetermined coefficients. So let's start with the guess for YP. And so I know, we just did a couple examples where, we solved the homogeneous solution first. Normally that's what you would do. But, because we're going to be doing this all in symbols, we're basically going to assume that we don't have any issues with matching. Okay, so for YP, let's guess. Okay. Since our forcing function here is a sinusoid function, F0 cosine omega t or omega x, then our guess has to also be sinusoids of the same frequency. And I keep switching between x and t. So this should be omega x, omega x. Sorry about that. My mind wants to say time t, but I've been using x, and so I need to be consistent to use. Okay, so let's compute YP prime. So YP prime, we're going to take the derivative. So we have a minus a omega sine omega x plus b omega cosine omega x. And we have YP double prime, so minus a omega squared cosine x minus b omega squared sine . All right, so now that we have our guesses and their derivatives, we can go ahead and plug this back into our original equation. We're going to plug all these back in here. And so if we do that, we get m times minus a omega squared sine x b omega squared sine omega x. Okay, so c times minus a omega x plus b omega cosine x. That's k a cosine x plus b sine x equal to f naught cosine Okay. Alright, so it is a bit complicated just because we are working with all symbols right here. But I'll kind of show you the reason why we're working with symbols in a second. Because what we're going to do is that what A and B here represent, if we look back at our particular solution, A and B represent the magnitudes of those oscillations, right? And so our particular solution is a cosine function and a sine function, and then their magnitudes are A and B. Okay? So the reason I'm kind of doing everything in symbols right now is because in the end, when we solve this system, we're going to get a formula for the magnitude of the cosine term and the magnitude of the sine term. Okay? And then from that formula, we're going to be able to kind of show you kind of where the resonance basically comes from. All right. And so let's do the same thing here. And so let's distribute. And combine like terms. Right, if we do that, and so our two like terms here are going to be the sine and cosine, and so we're going to group the terms based on that. And so for the cosine, omega x, you get the function a minus m squared plus k plus c omega times b plus minus a omega times c plus b minus m omega squared plus k. Okay, and this is all multiplied by sine omega x. And all this is equal to f naught cosine x. And so it's kind of a mess. And so, that kind of usually happens when you're working with all variables. Okay. Yeah. All right. But in theory, we have two equations here, right? So we can form an equation with the cosine. Okay. So we can basically set this entire thing equal to f naught. And the other thing we can do is we can set this entire equation and set it equal to 0 because there's no sign on the right hand side. Okay. All right, and so if we solve both equations for A and B, we end up with the following expressions. So let me write down B. So B is actually not that bad. Okay. So B is equal to f naught c omega divided by k m squared 1b squared plus c squared omega squared. And so B, remember, this is the magnitude for the sine term. Okay. And then we have A, and A is kind of a monstrosity. So A is going to be equal to f naught c omega divided by k minus c omega squared plus c squared omega squared multiplied by k minus m omega squared all divided by c. All right, so let me as you guys are writing this down, I know this looks very scary. But it is not something that you need to memorize at all. So the main reason I'm showing you these equations is I want to show you kind of features of these equations that show you kind of where resonance is going to occur. Okay, but this is not something, when the midterm comes around, don't put this on your cheat sheet. I'm not gonna ask you to plug into this formula or memorize it to any degree. This is purely just to kind of illustrate what resonance is and kind of where it comes from. Okay. But we'll just kind of write it in for now, just so that we can. All right, any questions on just any of this so far? Everyone keeping track what all the symbols mean, okay? Oh, we have to look back at the notes. Okay, see, it's a lot of symbols. I'm gonna make one substitution just to make things a little more clear. And so what I'm going to substitute is the natural frequency of the system. Okay. And so we actually went over the concept of natural frequency. I think it was on Tuesday, actually. And so if you have a mass spring system without any damping, right? And so you have just a match attached to a spring. And we know that if you don't have any damping and you excite the system, the solution is just going to oscillate forever. Okay. And so the frequency of that oscillation, remember, we call that the natural frequency. And so this is for an undamped mass spring. Okay. And so what we found was that if you have an undamped mass spring, then the system is going to vibrate naturally at frequency of square root K over M. But remember, K is our spring constant and M is our mass. So the square root of that quantity of those two divided, that is going to be the natural frequency of the system. Okay. And so what we're going to do is we're going to use this natural frequency because we have so many symbols here. So we have F, C, omega, K, M, C, all that stuff. Okay. And so basically everywhere that we see K and M in the system, or everywhere that we can, we're going to plug in for our natural frequency. So let's go ahead and try case. All instances A with mega 0. And so doing that should make things a lot more clear. And of course, there's a lot of algebra that's involved in this step that I'm not going to show. Part of this is that you're gonna have to trust me on. But this comes from the text, so it should be reliable in theory. Okay. So let's look at A first. And so A, when you make that substitution, we get M times omega naught squared minus omega squared, all divided by squared times squared minus omega squared, 20 squared plus C squared omega squared. E is equal to F naught is C divided by M squared omega squared plus C squared omega. Remember, this is the amplitude cosine. It's the amplitude All right. And so from these equations, the main thing I want you to look at here is, we have our natural frequency, omega naught. Okay. So remember, the natural frequency, that's something that's built into the system itself. Okay, so every physical system, based on its mass and based on its stiffness, based on the spring constant, that's always going to vibrate at a certain frequency. Okay, so that's kind of built in. We don't really have control over that because that's just how the system is. That's how the system physically is. Okay. What we usually do have control over is the omega. Okay. So remember, omega without the naught, omega is our forcing frequency. But remember, one way we can define this is that that's the frequency at which we're kind of externally providing energy, we're externally forcing the system. Okay. Okay. Remember what we talked about kind of before we launched into this kind of alphabet soup of variables, right? Resonance will occur when the forcing frequency is either the same as the natural frequency or starts to get close to it. Okay. Right. So when the forcing frequency starts to match the natural frequency of the system, then resonance will occur. Okay. So let's look at our equations here and let's see if that's true or not. Okay. So let's look at A first. Okay. So A we have kind of this A is the one that's a little bit more complicated. So we'll talk about this one. So A, we have omega squared, excuse me, omega naught squared minus omega squared up top, okay? M omega naught squared, okay? And so what's going to happen to this numerator as omega approaches omega naught, right? So as omega approaches omega naught, this right here is going to approach 0. So we know our numerator there is going to approach 0. All right, so let's look at our denominator now. Okay, and so in our denominator, we also have kind of the same thing. So we have an omega naught squared minus omega squared. And so this is also going to approach 0. Okay. But the big difference here is that in the denominator, we not only have omega naught squared minus omega squared, we have omega naught squared minus omega squared quantity squared, right? And so this square right here actually makes a big difference, okay? And so the difference is that, because we have the square in the denominator is going to approach 0 faster than the numerator. What does that mean? And so basically, as omega approaches omega naught, right, we have, on the one hand, we have the numerator that wants to take the amplitude down to 0, but the denominator is like, hang on, cowboy, I'm going to go down to 0 faster than you. And so what ends up happening, and usually we can assume that the second term of the denominator, the damping is usually fairly mild. Okay? The thing that's really going to dominate this is going to be those omega squared minus omega naught squared. Okay? And so when you have a situation when your denominator is approaching 0 faster, then what's going to happen to this entire A is that as omega approaches omega naught, then this entire thing will start to increase, pretty rapidly. And that makes sense, right? And so, what we tend to expect is that as the forcing frequency matches the natural frequency, then we start to get large amplitude oscillations, because that's what resonance is. Okay? And so, mathematically, what we can see here is that kind of checks out. All right, really quickly, let me show you B. So B is actually a lot faster than the A. Okay, and so for B we had F naught times omega C times or divided by M squared, omega naught squared, minus omega squared, 1B squared, plus C omega C squared omega squared. All right, so once again, we have in the denominator here, where this will start to approach 0. As omega naught, okay? And so once again, you have a situation where your amplitudes, the A and the B, is going to magnify as the forcing frequency gets close to the natural frequency. All right. Right. So in the homework, to kind of answer the question of the wine glass, you don't have to have a very loud voice in order to shatter a wine glass. The only thing you have to do is you just have to make sure that your pitch or the frequency of your voice matches the natural frequency of the wine glass, and you can shatter it even with a whisper. Okay. And then problem 4, I'm going to have you look at resonance again, but in terms of building design and earthquakes. So there's a little bit more. All right, any final questions before we wrap it up for today? Yeah.
So our homework is to shatter a wine.
If you do that and you film it, I'll give you a little bit extra credits. but don't waste a lot of money. So don't go to Daiso and buy like a ton of wine glasses. But if you can already do it, then that's pretty impressive. Any other questions? Yeah.
So like from an engineering perspective, are we always trying to like avoid resonance, or
Yes.
is there any case where we want to achieve it?
If you're in demolition, you want to achieve resonance, but most of the time you're designing things to not break, and so you're usually avoiding resonance. Okay, all right. So thank you guys. I know I went over time a little bit again today, so I apologize for that. But that's it for our ODE review. So actually next week we're going to start something new. It's called a loss transfer. Right? Hope you guys have a good weekend. Thank you guys for coming out today, and I will see you next week.
She goes like that's that.
I did ask.
But after. Are you seeing that stuff again? You're gonna use other stuff. It's gonna get complicated.
Yeah. Dudes, yeah.
What does it want?
It's like, it's different file. Oh.
And so you put that zero, you look back at all, there's no constant.
That's the notes.
So you end up with a constant.
Now speaking about paper. What's separate? Yeah.
Yeah.